Hello, my name is Hans van Leunen. I'm a retired physicist. I spent my career in high-tech industry. This lecture introduces you to the Hilbert Book Model project. The Hilbert Book Model represents my personal view on the lower layers of fundamental physics. The model deviates considerably from the models that together constitute contemporary physics. The model is largely deduced. For that reason, it is strictly based on a well-accepted foundation. The Hilbert Book Model selects quantum logic for that purpose. As a consequence, the underlying space progression model becomes paginated. It consists of an ordered sequence of static submodels. I started my investigations during my studies in the 60s, when I wondered about the strong differences in the way that classical physics was done and the way that quantum physics was done. I also wondered about the fact that observables were restricted to integers or real numbers, while our world is obviously a 3 plus 1 dimensional structure. In those years I was able to partly resolve these questions. After my studies, I started my career in high-tech industries in the development of image intensifiers. There I was intensively confronted with quanta. On the output screen of these devices I could only see hailstorms of impinging quanta. I did not observe any sign of impinging waves. This intrigued me, but there was not much time to deliberate about these facts. It had to wait until after my retirement until I got sufficient time to restart my investigations. In 2009, when I was 68 years old, I started a personal research project that in 2011 got its final name, the Hilbert Book Model project. Physical reality is like a peep show. No model of physics can fully describe physical reality. At the utmost, a model offers an abstracted view. That is all information that we get via the corresponding peephole. Physical reality appears to pose strict rules for the relational structures that it tolerates. The rules reduce the complexity of the supported relational structures. Physical reality is very complicated. However, views on reality that apply sufficient abstraction can be rather simple. It is astonishing that such simple abstractions exist. Complexity is caused by the number and the diversity of the relations that exist between objects that play a role. These rules can be formulated in axioms. Together these axioms define a skeleton relational structure. In 1936 the duo Garret Birkhoff and John von Neumann defined their idea of this skeleton and called it quantum logic. They also showed that the skeleton relational structure is isomorphic to the set of closed subspaces of an infinite dimensional separable Hilbert space. It is false to think that physical reality is based on mathematics. But it can be concluded that physical reality shows relational structures that also appear in mathematics. That is why mathematics fits so well in the formulation of physical laws. Physical laws appear as repetitive, recognizable structures and phenomena. Classical logic and quantum logic describe relational structures of sets of propositions that can act as skeleton relational structures. The content of the proposition is not part of the specification of the axioms. The specification of the axioms does not contain means to implement dynamics. The Hilbert Book Model is strictly based on traditional quantum logic. This foundation has the same relational structure as a set of closed subspaces of an infinite-dimensional separable Hilbert space. The first level of the Hilbert Book Model uses an infinite-dimensional separable quaternionic Hilbert space. The Hilbert space operators have a countable number of eigenvalues. This first level only implements a static status quo and it cannot implement fields. At the first place, the first level model does not support continuums. Hilbert space operators have countable eigenspaces. At the second place, the first level model does not support dynamics. This level can only represent a static status quo. At the third place, the Hilbert space contains deeper details than quantum logic does. Quantum logic propositions conform to subspaces of the Hilbert space. Refined propositions conform to Hilbert space vectors. The logic objects conform to objects in Hilbert space. On their turn, these objects conform to objects in the physical model. The isomorphism introduces a set of particles where each particle is represented by a swarm of stepstones. Particles are represented by atomic quantum logical propositions. Stepstones are represented by Hilbert space vectors that are eigenvectors of operators of the Hilbert space. The congruence between the relational structures is not complete. Propositions conform to Hilbert space subspaces. With its vectors, the Hilbert space offers extra details. So refine quantum logic to Hilbert logic. That refined version is a nearly direct replica of the Hilbert space. The Hilbert space can still not represent continuums. So add the Gelfand triple to the Hilbert space. It features operators that have continuums as eigenspaces. These continuums can be used to implement fields. The model must support discrete sets as well as continuums. In order to be able to represent the static status quo of the universe, both the quantum logic model and the Hilbert space model are extended. The submodels are static. A dynamic model consists of an ordered sequence of these submodels. The solution is an ordered sequence of static submodels. The result looks like the sequence of the pages of a book that each describes a static status quo of the whole universe. That's why the model is called the Hilbert Book Model. The sequence contains a prehistory, a reference submodel, a previous history, the current submodel, and the future. We will select a state of highest packaging as the reference submodel. The eigenspace of the reference enumeration operator is flat. The corresponding Gelfand triple will deliver the reference continuum which is eigenspace of the corresponding enumeration operator in the Gelfand triple. The resulting dynamic model is a paginated space progression model. A paginated space progression model uses a model-wide clock. In the Hilbert Book Model, the speed of information transfer is a constant. The step size is a smooth function of progression. Space expands or contracts in a smooth way. The model proceeds with universe-wide progression steps. The progression step size is rather fixed and corresponds to a super high frequency. The super high frequency is the highest frequency that occurs in the model. In a paginated space progression model, the model can be considered to be recreated at every progression step. If no other measures are taken, then the model will represent dynamical chaos. In order to prevent dynamical chaos, an external mechanism must establish sufficient coherence between subsequent steps. A too stiff coherence will prevent that dynamics occurs. The countable eigenspaces of Hilbert space operators and the continuum eigenspaces of the Gelfand triple can act as storage places of information that changes with progression. The eigenvectors store the corresponding relations. Storage places contain information that changes with progression. That information concerns content of logic propositions. In order to avoid dynamical chaos, the correlation vehicle must install sufficient coherence between subsequent members of the sequence. However, the coherence must not be too stiff, otherwise no dynamics occurs. The correlation mechanism uses the properties of the static submodels in order to implement its task. It applies the eigenspaces of operators as storage places. It applies a blurred allocation function in order to offer allocation to the particles. It uses the Huygens principle in order to control the spread of the influence of the singularities that are caused by the embedding process. Its functionality requires the ability to identify the atoms of the quantum logic system. This will be implemented via an enumeration scheme. The enumerator mechanism must not introduce extra functionality or properties for the enumerated objects. The correlation vehicle must be able to identify the atoms. This will be arranged by an enumerator mechanism that uses the eigenvalues of an operator in the isomorphic companion of the quantum logic system. The action of the operator can be described by an enumerator function. Both the operator and the function produce rational quaternionic enumerators. The enumerator operator is not a common normal operator. The allocation operator corresponds to an allocation function that uses rational quaternionic enumerators as its parameters and q-targets as its images. The blurred allocation function is the convolution of the sharp continuous allocation function and a spread function. Locally, the enumeration produces a q-pattern that acts as a blur and is deformed by the sharp part of the enumeration function. Like the overall blurred allocation function, the sharp allocation function uses rational quaternionic enumerators as its parameters. The sharp allocation function produces planned q-patches as its targets. The spread function parameters create a q-pattern. The overall function creates q-targets that together are described by a QPDD. A QPDD is a quaternionic probability density distribution. Q-targets exist only at a single instance. At that instance, the corresponding object can be detected at that location. This corresponds with the idea that the enumeration generator generates only one enumerator of the q-pattern per progression step. The subsequent q-patches are locations that are smoothly but non-uniformly positioned in a multidimensional curved continuum. Swarms define the local shape of the blur. The swarm is deformed by the local space curvature. Q-patches indicate the location of the swarm. Constantin Piron and Maria Pia Soler have proved that Hilbert spaces can only adapt members of a division ring as the numbers that can be used for the specification of the inner products. This then also holds for the eigenvalues of linear operators. Only three number systems form suitable division rings: the real numbers, the complex numbers, and the quaternions. Quantum physics uses a special kind of swarming that is determined by four swarming conditions. A swarm is a coherent set of stepstones. A swarm can be described by a continuous object density distribution. That density distribution can be interpreted as a probability density distribution. A swarm moves as one unit. In first approximation, this movement can be described by a linear displacement generator. This corresponds to the fact that the probability density distribution has a Fourier transform. The swarming conditions result in the capability of the swarm to behave as a part of an interference pattern. So these swarms are special kinds of swarms. The swarming activity of the correlation mechanism can be characterized by a mapping quality characteristic. The Fourier transform of the density distribution that describes the planned swarm can be considered as the mapping quality characteristic of the correlation mechanism. This corresponds to the optical transfer function that acts as a quality characteristic of linear imaging equipment. It also corresponds to the frequency characteristic of linear operating communication equipment. The Fourier transform of the spread function is a quality characteristic. The curvature of the target space also determines the quality of the produced image or map. By requiring that the two sides of the quaternionic differential equation contain normalized functions, this equation turns into a coupling equation. Since swarms move as one unit, a displacement generator exists that describes infinitesimal movement. This means that the quaternionic nabla forms a coupling equation. A large part of the task of the correlation mechanism is the recurrent recreation of swarms. The correlation mechanism generates swarms of stepstones in a cyclic fashion. The swarm is prepared in advance of its usage. This planned swarm is a set of placeholders that is called Q-pattern. A Q-pattern is a coherent set of placeholders. The stepstones are used one by one. In each static submodel, only one stepstone is used per swarm. The stepstone is called Q-target. When all stepstones are used, then a new Q-pattern is prepared. The blurred allocation function P, which is the convolution of P and S, uses the rational quaternionic enumerators that are taken from the reference continuum as its parameters. First, the stochastic spatial spread function S is used to generate the Q-pattern, and then the sharp allocation function P is used to map the Q-pattern to the embedding continuum. This delivers the actable swarm. Next, via random selection, the next stepstone is selected. The stepstone becomes the Q-target. At each progression step, a new stepstone is selected in order to become the current Q-target. In fermions, this stepstone is not used again. After consuming all stepstones, a new Q-pattern is generated. The Q-patches form a movement path. The Q-targets form a micropath. The micropath stretches along the particle's movement path. Building blocks are represented by a coherent set of stepstones that are generated by a stochastic process. The stepstones are placeholders of locations where the building block can be. The stepstones form a stochastic micropath. At each progression step, a new stepstone becomes the Q-target of the building block. The Q-pattern covers a fixed number of stepstones that together form a stochastic micropath. The micropath stretches along the movement path of the building block. An event means the generation, annihilation, or the sudden energy change of a building block. The solution is found in randomizing the low-skilled enumeration process. After sufficient enumerator generations, any order will be destroyed. A stochastic enumeration generator is implemented by a Poisson process. That process is attenuated by a binomial process that is installed by a three-dimensional spread function. The result approaches a three-dimensional Gaussian distribution. That distribution corresponds to a potential that off-center has the shape of a single charge gravitational potential. Now the enumeration function gets a double functionality. It describes space curvature via the differential of its sharp part, and it describes the local blur that is caused by the random enumeration process. When the swarms are relatively static, then the pattern corresponds to a single charge gravitation potential. Even at rest, the building block walks along its micropath. The duration of this walk is fixed. The micropath is stretched along the movement path of the building block. Thus the building block walks its path in a stochastic way. The micropath has a fixed cycle time. After that cycle, the set of stepstones is regenerated by the stochastic process. Only the statistical characteristics of the set keep the same. At every arrival at the stepstone, the building block emits a wavefront that carries a message about its presence and its properties. These properties become visible in the potentials that are formed by the wavefronts. A dedicated Green's function describes the contribution of the wavefront to the potential. The emitted wavefronts leave the building block and no longer affect the building block. Still, they offer noticeable traces of the existence of the building block. Together, the wavefronts form super high frequency waves. The average effect of these super high frequency waves form the potentials of the particle. The palestra consists of the embedding continuum, which is covered by a discrete set of Q-patches. These are swarms of singularities that represent particles. The blurred allocation function is the base of both a quaternionic gravitation theory and a quaternionic quantum physics that is based on quantum fluid dynamics. Classical logic and quantum logic are relational structures. They are also called lattices. Lattices are defined by a set of axioms. Lattices are partially ordered sets. Partially ordered sets are defined by a set of axioms. An orthocomplemented lattice is a special kind of lattice. A distributive lattice obeys the distributive law. A modular lattice obeys the modular law. Classical logic is an orthocomplemented modular lattice. A weak modular lattice obeys the weak modular law. Atomic lattices contain atomic propositions. Classical logic has a structure of an orthocomplemented distributive modular and atomic lattice. Quantum logic has the structure of an orthocomplemented weakly modular and atomic lattice. It is also called an orthomodular lattice. The set of closed subspaces of an infinite-dimensional separable Hilbert space forms an orthomodular lattice. It is lattice isomorphic to quantum logic. In order to get the Hilbert logic, add linear propositions. Linear propositions are linear combinations of atomic propositions. Add the relational coupling measure. The relation coupling measure is equivalent to the inner product of the Hilbert space. Closed subsets with respect to relational coupling measure. Propositions correspond to subspaces. Linear propositions correspond to Hilbert vectors. The superposition principle in Hilbert logic means that linear combinations of linear propositions are again linear propositions that belong to the same Hilbert logic system. Lattice isomorphic means propositions correspond to closed subspaces. Topological isomorphic means linear atoms correspond to Hilbert base vectors.